sketch. So for this case, right, you have a combination of shear stress and bending moment. Okay, so the position to check is over here, because this is your failure point. Okay, when you have a combination of normal stress and what? Shear stress. So that is where you're going to check where failure will occur. Okay, so now we're going to draw. So we're going to find shear. The formula is very we know is VQ over IT. So we know that V is equal to 80 times 10 power 3. We know that I is, so we know our I value, right? It's given in the table. I is equal to 40.1 times 10 to the power minus 6 meters. Okay. And then we're going to find our T. So T we also know is the thickness of the web. So thickness of the web is 6.35 times 10 to the power minus 3. Right? So what we need to find now is the Q for the flange. Okay, Q for the flange. So Q for the flange is equal to width multiplied by depth y bar. Okay, so the width that we already know is 0.102. The depth of the flange is what I'm looking at. The depth of the flange. Can someone tell me what's the depth of the flange? It's 10 millimeters, right? So 0.01, right? And then the y bar is 0.259 divided by 2 minus by 0.01. I hope you guys have not forgotten this, okay? And you guys said, oh, not again, right? So this will be equal to 0.259 divided by 2 minus by 0.01 divided by 2. By the way, we are still marking your term test, okay? We are not finished yet. So you get 126.99 times 10 to the power minus 6 meter cube. Okay. So the shear at 0.8 distance is equal to 80 times 10 to the power 3 divided by I, which is 40.1 times 10 to the power minus 6 multiplied by 126.99 times 10 to the power minus 6, and then divide by 6.35 times 10 to the power minus 3. So this will be equal to 80 power 3 times 126.99 power minus 6 divided by 40.1 power minus 6 divided by 6.35 power minus 3 is equal to 39.897 times 10 to the power 6 Pascal. Okay, I'll do it again. So 80 power 3 times by 126.99 power minus 6 divided by 40.1 power minus 6 divided by 6.35 power minus 3. Continue. Yep. Okay, so now we look at our normal stress at 0.8. Right, so the moment is 16 times 10 to the power 3. The the I is 40.1. And then the Y, okay, so from the centroid, right, so we need to find this Y distance, right? So the Y is equal to 0.259 divided by 2 minus by the flange thickness, which is 10 millimeters, 0.01. Okay. So 16 power 3 times by 0.259 divided by 2 minus 0.01. Okay. And then divide by 40.1 power minus 6. So it's equal to 47.68 times 10 to the power 6 Pascal. And the way there is bending, so if you look at this structure, how you bend, it will bend this way, right? So we know that this will go down, so you'll do this. Okay, so that's how the deformation look like. So when it is at 0.8, right, it's going to be at tension. Okay, so down here, so we're at the top point or the bottom point. That's not, so top point, the bottom point does not matter. So we can have it tension or compression does not matter. Okay, because it's axis symmetry. Right. So this is 47.68 times 10 to the power 6 Pascal. And that is our normal stress and shear stress. So we know that the failure point will be over there. Okay, now let's look at when Z, okay, when Z, so we're going to check. So just put the values over there first. Okay, don't do anything. So we're going to check when Z is equal to what? Z is equal to 2.4 now. Okay. I'm going to draw a line here so we can. By the way, today's quiz, I'll give you time up to Friday at 6 p.m. to submit. Okay, I know it's Canada Day, so some of you want to relax a bit. I understand. Okay, so we submit your quiz on Friday at 8 p.m. How's that? Okay, right. So we know that V is equal to 0 now, right? That's 0. Okay, then we have our moment. It becomes a maximum. Right? So for this case, because your shear is equal to 0, right? You can see that the shear is equal to 0. The failure will be where? Will be over here. This is where M max will occur, yes or no? No more failure over here, right? You don't choose the junction anymore, right? Because you have 0 shear stress. The failure is going to be based on what? Normal stress. So if it's going to be based on normal stress, it's going to fail at the what? At the position where Y, where this is your Y max. Can you see that? So you have to be very, very cautious where you calculate your maximum or your normal stress or your shear stress or any of this. Okay, you understand what I mean? Because your shear force is equal to what? 0. Right? So the failure will not be a combination of normal stress and shear stress. Your failure will occur based on what? Based on moment where the Y is at the maximum. So for this case, it's equal to stress at 2.4 or the shear. Okay, let's look at the shear at 2.4. So the shear at 2.4 is equal to 0, right? 0 shear stress. The normal stress at 2.4 is equal, so moment is 48 times 10 to the power 3, right? So divide by 40.1 times 10 to the power minus 6, right? And then minus, multiply by 0.259 divided by 2. Okay. So 40 power 3 or 48 power 3 times by 0.259 divided by 2 divided 40.1 power minus 6. So is, let me do it again. 48 power 3 times by 0.259 divided by 2 divided 40.1 power minus 6 is equal to 155. So I get 155.012 times 10 to the power 6 Pascal. Whoa, this is a high number, yes or no? Right? So you check. So we now know by just viewing this, right? We know that failure will not occur at point Z, right? Because your normal stress is at where? 2.4. Okay. Even though you combine this, okay, you combine this to find the principal stress, it's no way going to be higher than 155. Okay. So now, what you realize that the normal stress is 155, the shear stress is equal to 0. So this over here, right, can be a principal stress. Because the shear is equal to what? 0. Okay? So it's a 155 now, right? So when we started our question, we say what? The stress that the structure is able to withhold, the allowable is 160. So 155 is pretty close, right? So now the next one we're going to check when Z is equal to we're going to check where Z is now equal to 3.2 meters. And now your V is equal to 40 times 10 to the power 3. And then your M is equal to 32 times 10 to the power 3 Newton meter. So for this case, right, we are going to check where? We're going to check at this failure point now. We're going to check exactly as here because now we have a combination of what? Okay. So now we have a combination of normal stress and shear stress. So when you have a combination of normal stress and shear stress, the failure will occur at the junction. That is your failure point. You cannot pick the top. Why? Because your shear stress will be equal to 0. No doubt you have V equal to 40 times 10 to the power 3, right? Okay. So we're going to check shear 3.2, 40 times 10 to the power 3. Your first moment of area is still the same, is 126.99 times 10 to the power 6 or minus 6. Thickness is 6.35 times 10 to the power minus 3. And then your I is 40.1 times 10 to the power minus 6. Okay. So this will be equal to 40 power 3 times 126.99 power minus 6 divided by 40.1 power minus 6 divided by 6.35 power minus 3. So it's equal to 19.948 or 949 times 10 to the power 6 Pascal. And then your normal stress 3.2 is equal to 32 times 10 to the power 3 divided by your I value is 40.1 times 10 to the power minus 6. You calculate where the failure will occur. So this will be equal to 0.259 divided by 2 minus by 0.01. Okay. So 30 to the power 3 times by 0.259 divided by 2 minus by 0.01 divided by 40.1 power minus 6 is equal to 95.361 or 362 times 10 to the power 6 Pascal, right? So now we don't. So the problem with this is at Z equal 3.2, that's not the principal stress. Okay. So the next thing we have to do now, we have to apply Mohs circle now. Okay, we have to apply Mohs circle. So what have we calculated? Okay. If we go back to an element, we calculated that over here you have a tensile. Now tensile compression is the same for this case because it's symmetrical loading. Okay. So we have not symmetrical, the geometry is symmetrical. Okay. So we have 95.362 times 10 to the power 6. And then you have a shear, right? Your shear is going at 19.949 times 10 to the power 6. Okay. So if we follow our transformation, This will be our Y. This will be our what? Our Z. Okay. So now we have to find the principal stress.